We will continue our introduction to cellular energetics in order to summarize the ways in which the laws of thermodynamics are used to describe free energy. Thermodynamics can be defined as the study of energy changes in chemical reactions and physical processes. Thermodynamics help one determine if a reaction will occur. It also tells us the direction and degree of a reaction. However, it does not tell us how fast a reaction may occur. That would be kinetics. We will focus on the first two laws of thermodynamics. The first law is a law of energy conservation. It states that the energy is not created, nor is it destroyed. Instead, the total energy in a system is constant. This implies, then, that the form of energy is transformed from one state to another. Energy can also be stored in a system. The first law measures a change in energy by the flow of heat from one form to another. The heat in a system is enthalpy, and the change in heat is calculated as delta H. When calculating the delta H, if the value is greater than 0, the system absorbs heat and is endothermic. If the delta H is less than 0, the system releases heat and is exothermic, meaning heat out. Shown is a representative plot of the energy for each type of reaction to compare the potential energy of a reaction over time and the conversion of reactant into products. For exothermic reactions, you may notice that there's a greater potential energy in the reactants and lesser in the products. A real example of this in cell biology includes the processing of pyruvate into acetyl-CoA during cellular respiration, a topic to be covered later in this unit. On the other hand, endothermic reactions require energy to be absorbed by the reactants to form the products, which have a greater amount of potential energy. An example of this in cell biology is at the start of glycolysis. Glucose is phosphorylated by ATP to form glucose 6-phosphate. The second law of thermodynamics states that all energy transformations have directionality and are inefficient. This is measured by the entropy, represented by the letter S, in a system. Entropy is often described as being the amount of disorder and randomness in a system. Some examples of entropy increasing in systems are provided by this TED-Ed presentation. They include ice melting, coffee creamer dissociating, and air flowing out of a punctured tire. The first two laws are put together in Gibbs free energy. This describes the change in energy which is available for work. In other words, it considers both entropy and enthalpy. One could use the delta G to calculate the change in heat in the formula delta H is equal to the delta G plus the product of temperature and change in entropy. Rearranged, we could find the delta G is equal to the change in heat minus the product of temperature and change in entropy. In other words, the delta G value measures the spontaneity of a reaction. So all spontaneous reactions result in a decrease in the free energy of the system. Lastly, the delta G is negative for any real or spontaneous reaction. We can again look at plots to represent the delta G as a reaction progresses from the conversion of reactants into products. Reactions where the delta G is less than 0, they are spontaneous and likely to occur. As a reaction proceeds, energy is transferred out and the reactions are called exergonic. Reactions with a delta G greater than 0 are not spontaneous and will need an input of energy to transform reactants into products. These reactions are called endergonic. An example from the textbook are the changes in water in its transformation from very cold ice to warm liquid water. Turning our attention to the very end of the chart, we can see that the delta G of very cold ice is negative 54. This means that it's very likely for water at negative 10 degrees Celsius to transform from the solid state to the liquid state. However, it's unlikely for liquid water at 10 degrees Celsius to transform from the liquid state to the solid ice state, the delta G value of plus 154. In summary, thermodynamics studies the changes in chemical reactions. The first and second laws of thermodynamics give the direction, degree of disorder, and likelihood of a reaction to occur